What's going on, smart people? Today we are wrapping up the derivation of the Feynman path integral. I say we're wrapping it up, but this is going to be a long video. There is a lot to get through. We're going to do some weird shit, I'm going to be honest with you. But we're all going to be okay. I'm going to try to explain things in the way that I understand them as best that I can. I want to make this so that people who have some experience with quantum mechanics can follow the rest of the derivation with moderate ease, and people who are already familiar with the path integral can hopefully get something out of this as well. So let's go ahead and get started. As a refresher, because the last video was quite a while ago, we were interested in the propagator, which was effectively the matrix element of the time evolution operator right here, where we have this exponential minus I on h bar, the Hamiltonian, times some time parameter. And then what we did was we did the exponential equivalent of multiplying and dividing by the same thing. We divided by some parameter n and then raised it to the power n, so effectively we're not really doing anything. And what this does is it discretizes our time and space, but we'll get to that in a little bit. Since we're multiplying this by itself n times, we might as well write that stuff out, and while we did that, what we did was insert completeness, complete sets of coordinate bases, n minus 1 times. So that brings us to where we are now. For this video, one thing that would be nice to remember is we can have something like the momentum eigenstate in the coordinate representation, which is really just the transformation coefficient for a Fourier transform when looking at wave functions in position or momentum space, is just given by this 1 over root 2 h bar e to the I on h bar px. So this is something that if you've had quantum mechanics, this is nothing new. This stuff, don't worry about it yet. I just don't want to miss signs later on, so I have it up there. That's when stuff gets weird. So this is where we're at. We explicitly wrote out this exponential being multiplied by itself n times, and then we inserted completeness n minus 1 times. So we have n minus 1, minus 2, and so on all the way to x. And then we have to integrate over all of those complete sets. That way we're just multiplying by 1, sort of. Okay, so that's where we are now. The next thing, by the way, I'm sorry if you can hear my fan. It's like a bajillion degrees in New Mexico and it's August, and apartment complexes insist on using swamp coolers for some reason, which does nothing. The next thing that we want to do is sort of the same thing, except for we want to now insert complete sets of momentum states, and we're going to insert n of them this time. The reason sort of being, when we inserted complete sets of coordinate things, we inserted them here. Now we're going to also insert a momentum state here, which will give us n instead of n minus 1. So let's go ahead and do that. So now we're going to be integrating over our coordinates dx n minus 1 dot 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 dx 1 integral dp n minus 1. Since we're indexing with n minus 1, the p will end at 0 dot 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 dp 0. And then we're inserting our states. So we have an x prime p sub n minus 1, and then we have a p sub n minus 1, the exponential of the operator, e to the minus I on h bar h t over n. And then we're going to have, next would be an x sub n minus 1, x sub n minus 1, p sub n minus 2. Let's go ahead and do this n times. No, we'll just dot 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 for the rest. This keeps going on for the rest of the insertions. So then we'd have more of these and so on. Okay, well, we know what this is. This is just really this transformation coefficient, but with the appropriate subscripts and the primes and whatnot. The reason that we want to do this, the reason we're inserting completeness sets for position and momentum, is because our Hamiltonian operator is in terms of position and momentum. So it would be nice to have those acting on the appropriate eigenstates. That way, instead of operators, we're left with just numbers. That's one of the beautiful things about the Feynman path integral, is when you go through the derivation, you more or less get rid of operators in the formalism, and you're left with just the numbers, the eigenvalues. But in order to do that, we have to invoke something kind of subtle. This is one of those things where it's an equation, it's an identity, a relation that we're going to use that if I were to go through the derivation in this video, it would take the length of the video in itself. So if you're interested in seeing it, I'll absolutely leave a link to a derivation in the description, but if you want to see me do it for some reason, let me know in the comment section and I'll make a video on it. But we have this Hamiltonian operator. We have our h is some momentum operator squared over 2m plus some potential that depends on the coordinate operator, the position operator. Now, one thing that we're going to need has to do with the exponential of a sum. If we have like two numbers and we have, say, e to the a plus b, where a and b are numbers, we know that that's just equal to the product e to the a times e to the b. But if these aren't numbers, if, say, in our case, these may be operators, it's not that simple. We need something that contains the structure of these, of how these two things are related, like they're commutators. So there's something that's called the Trotter product formula that's heavily related to something called the Baker-Cambell Hausdorff formula, which contains that additional structure. It says that it should reduce to the case where these are just numbers. Let's make this look a little bit more like the operators that we have. So we're going to have a minus I on h bar, sorry, not on h bar, on n. Get to y in just a minute. Should be a minus I on n, minus I on n. Should be a 1 plus the terms that contain the commutator structure. So we have a commutator a and b over n squared plus the higher order terms, so 1 over, I guess, n cubed. This is something that sounds reasonable. It reduces to the case to where these are two numbers. If we're dealing with operators, there should be some relation that talks about how they commute with each other or how they don't commute with each other. But the derivation or the proof of this is not trivial in any means. It actually would probably take the length of the video that this already is just to prove this. So if you're interested in seeing it, let me know. But for now, we're going to take this for what it is. I'll leave links in the description. That way you can find derivations of this. But like I said, if you want to see me do it for some reason, just let me know. Okay, what this says is we're eventually going to let n go to infinity. And what that tells us is that if n goes to infinity, these commutating terms, these terms that contain the structure, they don't contribute anymore. If you look at it this way, if we had this in terms instead of like t over n, which we'll call like some, that's what I call delta t, right? It's not important for now, but if this is just some displacement in time, we're effectively, as n goes to infinity, having an infinitesimal displacement in time. So what this is telling us is as we let that infinitesimal displacement in time go to 0, these commutator terms don't contribute. This is completely analogous to if you've worked with infinitesimal generators of rotation or infinitesimal rotations in classical mechanics. Rotations as a whole don't commute with each other, but infinitesimally they do. So this is the same concept. And this is going to let us do something very helpful because it'll let us split this exponential of the Hamiltonian in terms of an exponential of the momentum term and an exponential of the position term, which is going to be exactly what we need. Great, so now let's write this in terms of that relationship now. So now we're eventually going to let n go to infinity, so the error will go away. For now, we're not letting n go to infinity, and we're just going to be neglecting those terms. So in your head, you can keep those error terms with you the entire time. In the back of our mind, we'll know they're there, but once we let n go to infinity, it won't matter. So this is just going to be equal to the integral dx n minus 1 dot 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 dx1 dp n minus 1 dot 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 dp0. This, let's go ahead and write this stuff out now. So this is just going to be a 1 over root 2 pi h bar, and then this guy, so it's going to be a piece of n minus 1, so we have an e to the I on h bar, piece of n minus 1 x prime. And then this matrix element, piece of n minus 1, e to the minus I on h bar, p hat squared over 2m times t over n, e to the minus I on h bar, v of x, t over n, x of n minus 1, And then the rest of the terms as well. X sub n minus 1, p sub n minus 2, dot, dot, dot. Okay. We have an exponential of operators. Maybe it would be helpful to talk about what that means in the first place. If we have an exponential of an operator, that's to be understood in terms of its power series. So if we were to have some operator e to the a acting on some eigenstate where its eigenvalue is a, this is to be understood in terms of its power series, which would be a, or 1 plus a hat plus 1/2 a hat plus dot dot dot. And when we act on that eigenstate, this is just going to give us a 1 plus a plus 1/2 a squared plus dot 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 a, which is just e to the a times the state. So with that knowledge, we can apply, since these are Hermitian operators, we can act to the left or to the right. So we'll have the momentum term act on the momentum eigenstate, and the potential term act on the coordinate eigenstates. And we're going to eventually, we'd be doing these for all of those matrix elements. So when we do that, this is going to give us, sorry if I'm blocking stuff, dx n minus 1 dot dot dot, dx1, dp n minus 1 dot dot dot, dp0, 1 over root 2 pi h bar, e to the I over h bar, p sub n minus 1, x prime. So since these are acting on the states, these are just going to be numbers now, and the eigenvalues are going to be these p sub n minus 1s and these x sub n minus 1s. So these are just going to be numbers now. You're not taking matrix elements of them, so we can pull them out of the inner product. So this is going to be e to the minus I on h bar, p squared sub n minus 1 over 2m times t over n, e to the minus I on h bar, v of x sub n minus 1 times t over n. And then we have the inner product of p sub n minus 1, x sub n minus 1. Again, we're going to use this identity. Since now we have effectively p dot x, the only thing that changes is this gets a relative minus sign, because it's like the reverse Fourier transform. So this is going to be a root 2 pi h bar e to the minus I on h bar, p sub n minus 1, x sub n minus 1. Great, I hope that was clear. Times all the rest, times all this stuff again. Let's do some simplifications. Let's make some stuff settle nicely. We have 2 of the same factor here. Let's go ahead and simplify. This is equal to dx n minus 1 dot dot dot, dx1, dp n minus 1 dot dot dot, dp0, 1 over 2 pi h bar. Both of these have a common factor of I over h bar, p sub n minus 1, and then we'll have that difference of x's. So it's going to be an e to the I on h bar, p sub n minus 1, and then x prime minus x n minus 1. That's this term. That's these two. And then we're also going to have this squared term, e to the minus I on h bar, p sub n minus 1 squared over 2m, t over n, and then the potential term. Okay, and now we have something that's free times all the other stuff, that's free of operators and just have the momentum eigenvalues and the potential that depends on the x ones. Cool. The next thing that we're going to do is we're going to ignore the potential term for now. The potential term matters when we actually want to solve a problem, because we're integrating over these x variables, but in order to actually do the integral, we have to have a specified potential. So we're going to forget about the potential term for now and just focus on what we can do something with, which is the momentum part. So I'm going to erase this stuff up here. So I'm going to make a little corner over here that just says what the potential term is so I don't forget it. So it's an e to the minus I on h bar, v of x sub n minus 1, t over n. And now what I want to focus on is the momentum term. Now in principle, in reality, we'd be doing these integrals, these momentum integrals for all n of them, but let's just look at the p sub n minus 1 for now. So we have an integral p sub n minus 1. We have a 1 over root 2, sorry, not a root anymore, over 2 pi h bar. And then we have an exponential. I'm going to stop writing e2 though. Let's go ahead and combine these guys into one exponential. So we have a minus I over h bar, p sub n minus 1 squared over 2m, and then we have a t over n. Okay, and this term, plus I over h bar, p sub n minus 1 times x prime minus x sub n minus 1. So this is what we'd like to do the integral of. And this is the most, in my opinion, this is the most important part of the derivation, because a lot of things start to come into question here. For one, is how the hell do you do this integral? And as we'll find out, or not as we'll find out, as I guess I'll tell you later on, the fact that we're able to eventually do this integral is what saves the path integral, in my opinion, because it makes it actually converge. Because if you think about it, as we're introducing more and more paths, as we let n go to infinity, there's nothing constraining that integral from blowing up. There's nothing forcing it to converge to anything as we include more contributions from different paths. And figuring out a way to do this integral will give us a factor that saves everything. I'm going to take a sip of coffee, because I've been talking to myself all day. Okay. The way that we do this is weird. It's pretty weird. It has to do with something called analytic continuation. If you're interested in it, any complex analysis book will have it towards the end of the book. But effectively what we're going to be doing is we're going to be going to imaginary time. And the thing is we have an integral, and this is going from minus infinity to infinity, of something that is oscillatory. We have this I times this momentum that we're integrating over. So for large and for really negative momentum, this oscillates wildly. One way of trying to salvage this is by asserting that those wild oscillations locally cancel. The other way of doing it is by going to imaginary time. And I'll show you what happens when we do that. So we're going to define t to be this minus I times tau. Now let's go ahead and substitute that in. So if we do that, we have a integral minus infinity to infinity dp sub n minus 1, 2 pi h bar 1 exponential. And then we have, so if t is minus I times tau, then we have minus I times minus I, which is just minus 1. So we have a minus, and then we're going to have a minus tau over n. What I'm going to call that is a delta tau. So this is going to be a delta tau over h bar p sub n minus 1 squared over 2m. Is there anything else that I'm missing here? I don't think so at first glance, no. T over n, we've got that. We've got the 2m, we've got the h bar. Cool. So instead of t, we wrote minus I times tau. So that minus I times minus I just gave us minus 1, which has a tau over n, which I redefined to be a delta tau. That's all we've done so far, and nothing changes on the next term yet. X prime minus x sub n minus 1. So what doing this transformation did is it allowed us to transform this oscillatory integral into something that looks kind of like a shifted Gaussian, which we can handle. Now this whole idea with analytic continuation is we weren't able to solve this for regular time. The idea is you have this transformation that relates the regular time to some complex time. We want to solve the problem in complex time, or Euclidean time if we're talking about quantum field theory, and then if we can find the solution, we try to transform back. So that's the idea. It doesn't always work. For quantum mechanics, it's completely fine. Once you go to quantum field theory, you kind of have to take it case by case, but we'll talk about that a little bit later. So the next thing that I want to do is I want to factor out all of this stuff. So this is going to be equal to integral minus infinity to infinity dp sub n minus 1 2 pi h bar 1 exponential, and we have a minus delta tau over 2m h bar, and then this stuff. So we have a p sub n squared, n minus 1 squared, and then all of the stuff. So we factored out an h bar, and that's about it. So this should get, we factored out a minus, this should be a minus I, we factored out a 2m h bar, so it should be a 2m here, and then over delta tau, and a mass term, or the mass is already there. So p sub n minus 1, x prime minus x n minus 1. Okay? And now what I want to do is I want to complete the square. And that's going to let us redefine variables, and we'll just be integrating a Gaussian. So this is equal to the integral minus infinity to infinity dp sub n minus 1 2 pi h bar exponential, and we have that minus delta tau over 2m h bar. Okay, and completing the square, so that's going to be a p sub n minus 1 minus I m over delta tau x prime minus x sub n minus 1 squared. And then, so if we square this is going to be negative times a negative, which is a positive. So we want to subtract, this is going to be an m squared, so we have an m delta tau over 2 h bar delta tau. Anything else there? 2m. Okay, times x prime minus x sub n minus 1 squared. All of that squared off. Okay, let me just double check. I don't want to make mistakes here. So that's going to be fine. We have a delta tau that survives. We have an m that's squared, cancels one factor, a 2h bar. That looks good to me. Okay, well this term doesn't depend on p sub n minus 1 at all, so we can pull it out of the integral. So this is equal to integral minus infinity to infinity. Let's just pull out all of the constant stuff. So we have a 2 pi h bar over 1 exponential of minus m over 2 h bar x prime minus x sub n minus 1 squared over delta tau, and then the actual integral dp sub n minus 1 exponential of minus well, okay, let's kill two birds with one stone. So now that this is out, all we have is this square scaled. So I'm going to define a new variable that I'll call u. So let's say that u is defined to be the square root of delta tau over 2m h bar p sub n minus 1 minus I m over delta tau x prime minus x sub n minus 1, and then du is just root delta tau over 2m h bar dp sub n minus 1, and we can just invert the square root to get dp in terms of du. So in doing that, we get this factor here, root 2m h bar over delta tau times the integral of du e to the minus u squared. Okay, and this is just going to give us a root pi because it's just a Gaussian. So this is going to give us a root pi. Bringing the final integral to b, so we have, this is going to be, the 2 goes to the bottom, so we have a 2 pi, we have a h bar, we have a delta tau over m, or under m, I believe. Is that correct? So we get the pi that goes in the denominator, the h bar, looks good to me. And then we have the exponential. Minus m over 2h bar x prime minus x sub n minus 1 squared over delta tau. Now this is something that we're going to get for each time that we inserted our complete momentum eigenstate. So this is going to happen n times. So at the end, instead of this square root, this quantity to the 1/2, we're going to have this quantity to the n halves. And that's the most important part, I think, of this derivation, because that's what constrains and forces the integral to converge. As we let n get larger and include more and more paths, we have this thing that constrains and forces the integral to actually give us something finite. And then also for each of these, for these integrals, we're going to have one of these exponentials that's just got the shifted coordinate here. So let's go ahead and plop this guy up here and reintroduce our potential term, and we're actually almost done. So going back to the original integral, we have this integral, we have our dx n minus 1 dot 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 dx1 integral. Now that we've done this one, we'll start at d p sub n minus 2 dot 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 dp0, and then we have this term, so we have a root m over 2 pi h bar delta tau, and then our exponential. So we have a minus m over 2 h bar x prime minus x sub n minus 1 squared over delta tau. And then now we can bring back our potential term, exponential minus I on h bar v of x sub n minus 1 t over n. Okay, let's erase this stuff now. And the potential. And then we're going to have the rest of the stuff, the rest of those momentum parts. So we have x sub n minus 1, p sub n minus 2, dot dot dot, all of the other stuff. So like I said, we're going to get one of these factors and one of these exponentials for each of these matrix elements times these transformation coefficients. And we're going to have n of those integrals. So instead of the square root, once we perform all of the p integrals, we'll have an n over 2. Okay, so this is equal to the integral dx n minus 1 dot 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 dx1, and then we have an m over 2 pi h bar delta tau to the n halves. And now we can combine this exponential term. We have an exponential of minus m over 2h bar. Do I want to do something yet? Let's go ahead and redefine or insert our delta tau definition here instead of having t here. So we got that. We've gotten x prime minus x sub n minus 1 squared over delta tau. I'm going to leave myself a little bit of space, and you'll see why in a bit. Minus, so we have a minus I and a t, but t is just minus I tau, so this is just going to be a minus delta tau over h bar v of x sub n minus 1. Okay, and then times all of the other guys, because we did this integral for all of them. The next thing is I want to multiply and divide by delta tau. So I want to do times delta tau squared, and I want to pull it out. So this is going to be equal to the integral dx n minus 1 dot 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 dx1 m over 2 pi h bar delta tau to the n halves. exponential. So I'm going to factor out this h bar and this delta tau. So we have a delta tau over h bar, and then we're going to have a minus m over 2h bar, x prime minus x sub n minus 1 squared over delta tau squared. You might be able to see what I'm doing here. Minus 1 over h bar v of x sub n minus 1. No, we pulled out the h bar, I'm sorry. Minus v of x sub n minus 1. Okay, so that's this guy. I close the exponential. The next thing that I want to do is I just want to substitute back in what delta tau is in terms of t. So delta tau is just tau over n, and tau over n is just, so we have delta tau squared is equal to tau over n, which is equal to, tau is just I times t over n, and I want to define t over n to be delta t. So this is just I times delta t. Okay? So I'm going to substitute this into my delta tau squared. So substituting that in, we're also going to substitute that into this guy here. This is equal to the integral dx of n minus 1 dot 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 dx1. This is going to be an mn, big N, over 2 pi I h bar delta t to the n halves. So we have explicit n dependence here, times the exponential of, now we have a delta tau, which is an I times delta t, I over h bar delta t. And I guess you should have all these dot dot dots, because these are being multiplied by the shifted guys as well. Sorry if this is all over the place, a little bit all over the place. It's hard to do this on just one whiteboard. Okay? Now here's the interesting thing that happens. Delta tau squared is just going to be minus delta t. So we have an m over 2 x prime minus x of n minus 1 squared over delta t squared minus v of x of n minus 1 times all of the other ones. This is just the discretized version of a Lagrangian. We have the kinetic term minus the potential term. So we can explicitly write this out. So the final solution for the path integral, including the limits and all, we have our x prime e to the minus I on h bar ht x is equal to, let's pull this guy out, let's do the limit, as n goes to infinity, of m n over h 2 pi I h bar delta t to the n halves times the integral of the product from I equals 1 to n minus 1, so that's just encompassing these guys, of this exponential, and we're going to have one for each term, so this is just going to be an I on h bar delta t m over 2 x I plus 1 minus xi squared over delta t squared minus v of I. There we go. And this, make sure I got my parentheses all good, this is the definition of the Feynman path integral. So what we have here, if we take this limit that n goes to infinity, you may see a shorthand in terms of this just being this delta t goes to an infinitesimal, so this just becomes an integral, and then we have an integral over time of something that looks like the Lagrangian, so this is just the action. So the shorthand notation version for this is the integral dx x of t e to the I on h bar of the action. But this is just a notation. So this little dx of t is a notation. This is how it should be understood. And there we have it. We have finally derived the Feynman path integral for quantum mechanics. Now that we've defined our path integral, I just have a few more comments that I'd like to make. The first one being on the measure. Now, if you were to do a regular Riemann integral, what do? You discretize your space, you evaluate your function at those points, and you add them all up, plus one more step, which defines the measure, and you multiply by the step size between those points, right? If you were to just add up the points, infinitely many of them, and add them all up, there's no reason to expect that to give you a finite answer, and you multiply that by that step size to bring you back down to finite results to actually properly define an integral. Now, how to define a measure for a path integral is not as easy. And sometimes you'll hear people say that the path integral is not rigorously defined. And if they say that about path integrals for regular old quantum mechanics, they're a little bit full of shit. Because one of the things that we did when we went through this derivation was we borrowed something from statistical mechanics or statistics, namely the Wiener measure, or Wiener, I don't know how to pronounce it. Some people just call it the Gaussian measure. And it has to do with stochastic processes, random walks, and people learned how to define a measure for these kinds of things. And this happened when we went to imaginary time. When we went to imaginary time, our oscillatory integral became Gaussian. And when we did that integral, it popped down these Gaussian factors. And this is what helps make our integral actually converge. So this is completely rigorous for quantum mechanics. How to do this for quantum field theory, you kind of have to take it case by case. But to be honest, I don't know enough about defining the measure for general cases in quantum field theory. I think that you can do it for Yang-Mills theories and maybe a couple of others. But for the rest, I really don't know too much about it. Maybe check the comment section to see if other people can shed more light. It's a huge rabbit hole that you can go down with when it comes to defining the measure, because that's what people go up in arms about. The second thing that I want to talk about is it's convenient to work in this notation, to work in the continuum limit, even though it's not to be taken literally. It should always be looked at this way. But if we go back to imaginary time, then we have this minus times the action. So one way of interpreting this, why do we not just get solutions that blow up anyways? When you go to imaginary time, I think it makes it a bit more clear, because if you have these really crazy paths that would correspond to really high action, this weighting factor, this e to the I times the action, or e to the minus the action, would go to 0 for those really energetic solutions, those really obscure paths. So the paths that really contribute to this probability amplitude are the paths that minimize the action. So one of the cool bits of physics that we actually use, that you actually recover from the path integral, is the principle of least action, which I always thought was pretty cool. But anyways, there's so much that you can talk about with this stuff. You can talk about specifically the measure stuff with Lebesgue measures and whatnot. Maybe we could talk about it later in the future. I don't know if people are interested. And let me know in the comment section if you enjoyed the video, or if you want to see particular stuff of this that I may have glossed over in a future video. I hope you guys enjoyed it. Let me know in the comment section if you did, and I'll see you guys there.